Hello everybody, and welcome to our video on properties of functions. So here we're just going to explore some different properties of functions that will come up throughout pre-calculus and calculus. The first one we're going to talk about is the average rate of change of a function y equals f of x as x changes from a to b. So this formula is given by f of b minus f of a over b minus a. So the way you can think about this is the change in y divided by the change in the x values. So that describes exactly what we want it to, average rate of change. The change in y divided by how much x changed. And of course, another way to think about this is as the slope of the line between 2 points on the graph. So if you have a function like this, and this is A, and this is B, right? Then if you take those 2 points here and draw the line between them, the slope of that line is exactly what this formula is telling you. Okay, so let's go ahead and just apply the formula here. Find the average rate of change of f of x equals 3 minus x all squared from a equals 1 to b equals 3. So here we're just going to plug into the formula. That's all there is to do, really. So f of b, which is 3, minus f of a, which is 1, over 3 minus 1. So now we just take these and plug in. So f of 3 means take my function f of x, replace x with 3. That's 3 minus 3 squared, minus f of 1, which is 3 minus 1 squared, all over 3 minus 1, which is just 2. 3 minus 3 squared is 0 squared, which is still 0, minus 2 squared over 2. That makes negative 4 over 2, which is just negative 2. Done. Now, this isn't really asked here, but if we drew the graph of this function, and as I mentioned in the last video, we're going to touch on transformations more in the future, but this is basically just a shift of this quadratic function here. So if x was 3, we would get 0 here. And so when a is 1, what do we get? We get 2 squared, right? So that's 4. And when b is 3, we get 3 minus 3 is 0. Well, that's exactly what we had there, right? So if we just draw this graph here, roughly, what this is saying is the slope of the line between these 2 points, the average rate of change, the slope of this green line is negative 2, which matches exactly what we see in the picture. So again, if you're asked to find the average rate of change, you're not really being asked to draw this picture. I just thought it's helpful to illustrate geometrically what's being described here from the formula. Okay, so a few quick definitions. A function is called increasing on the interval from a to b if for any x1 and x2 in that interval, where x1 is smaller than x2, then f of x1 is smaller than f of x2. That seems a little bit confusing at first, but it's really pretty straightforward, especially if we just draw it out and see what this looks like. So we'll draw something that is increasing, and so we know that means it's getting bigger to the right. So this definition, which is more precise than just saying, oh, it's increasing, says if you've got x1 and x2 inside this interval, then if the function is increasing, then f of x1, the y value for the first x, should be lower than the y value for the second x. That's all that says. Now, a function is called decreasing on the interval from a to b if for any x1 and x2 in ab, where x1 is less than x2, then f of x1 should be greater than f of x2. So again, that can seem a little tricky at first, but if we draw it, try that again. If we draw it, it should make sense. So this time we're going to draw a function that is decreasing. So maybe it starts up here and ends down here. So here, f of x1 is up here. And f of x2 is down here. Right, so exactly as we expect, right, what we're saying here is if the function is decreasing, the first x value gives you a bigger output than the second x value. Okay, and last in this little group of definitions, f is constant on the interval from a to b. If for any x1 and x2 in the interval a, b, f of x1 equals f of x2. We'll call the output c here. So this just means that the interval from a to b, the function takes the value c the whole time. So this is like something simple. If you had, say, f of x equals 3, and we're just going to assume that f of x equals 3 everywhere here, right? That just means that the y value you get, no matter what x you input, the y value is always 3. Right? For any x you plug in, you still get 3, right? That's all that says. Okay, so another definition. If a is in the domain of a function f, we say that the value f of a is a relative maximum of f. If there is an interval around a, so an interval x1 to x2 containing a, such that f of a is greater than or equal to f of x for every x in that interval. Okay, so let's see what that means in a picture. So here, this will be a, and we'll have our graph will look something like this. So the key thing about something being a relative maximum, relative, it doesn't say that it's the biggest point on the graph. It says that there's an interval around it where it's the highest point. So if we look at f of a here, that's this y value. This says is if I draw a little interval around here from x1 to x2, everywhere from x1 to x2 here, this is the highest point within that range, or within that domain, right? So within that restriction, this is the highest point. That makes it a relative maximum. It's not necessarily the maximum of the function overall. It's just the maximum in this little area. So if you can draw some interval around a, and it's the highest point inside that interval, it's a relative maximum. That's all that means. So basically, anywhere you see what looks like a little peak of a mountain top, that's going to be a relative maximum. Similarly, if a is in the domain of a function, we say that the value f of a is a relative minimum of f if there's an interval x1 to x2 containing a, such that f of a is less than or equal to f of x for every x in that interval. So again, when we look at this relative minimum, it doesn't say that it's the lowest point on the graph. It just says that it's the lowest point somewhere near there. So if I draw a little interval around here, let's say this is x1 and this is x2. Okay, clearly this point is the lowest point on the graph in between x1 and x2. That makes it a relative minimum of f. All right, now we're going to go to a slightly different topic. So even and odd functions. So this is an extremely important set of definitions here. They're going to come up repeatedly throughout this class and throughout the calculus series. Even and odd functions, knowing whether a function is even or odd can actually save us a lot of work on problems in the future, especially moving into Calc 2. So these are very important definitions to make sure you get down and understand. So let's take a look at what this definition for even says. A function is called even if for each x in its domain, f of negative x equals f of x. So what that means is, if I draw a picture of a graph, let's say we'll just draw the right side of the graph for now. So if I take an x value here, I should get the same y value when I take that negative x value. Right? I should get the same height. When I plug in x, I get the same y value as when I plug in negative x. Right? But that's got to be true for all x values in the domain. But that means that you're always going to get a mirror image over the y-axis. Right? That's what this says. So, fact, even functions are symmetric over the y-axis. If we know a function is even, we know its graph looks like a mirror image over the y-axis. Now, odd functions are a little bit different. So a function is called odd if for each x in its domain, f of negative x equals negative f of x. Okay, so here the picture looks a little different. So I've got x here, so let's say we'll draw our graph like this. So this is f of x. The definition of an odd function says, when I plug in negative x, I should get the negative of the y value that I had before. So that makes the graph look like a rotation 180 degrees around the origin point, around this point. It looks like every point is turned around 180 degrees facing this direction. So we call that symmetric with respect to the origin. Okay, so that's how you can interpret the graphs of functions that are even or odd. So let's take a look at some functions and determine algebraically if they are even or odd. So determine if the function is even, odd, or neither. Determine whether the function is increasing or decreasing as well. So that second part is going to be a little bit trickier, actually. Determining whether it's even or odd or neither is the easier part. Okay, so f of x equals x cubed. All we have to do is just check the definition directly here. This is something that gets overthought a lot, but what this definition says is, if I plug in negative x, the function is even if I can re-simplify it to look exactly like the original function, and it's odd if I can re-simplify it to look like the negative of the whole original function. And it's neither if you can't do either of those things. So we just plug in negative x into the function. So in this case, that's negative x in parentheses cubed. Remember, whenever you plug in something into your function, you should really be putting parentheses around it to make sure you apply your order of operations correctly. So here it's very important that this negative is paired with the x because the cube needs to apply to the whole negative value. Now, I'm going to go a little overboard here in writing this. This is really negative 1 times x cubed. And our exponent properties tell us we can write this as negative 1 cubed times x cubed. And when I cube negative 1, I just get negative 1 again. So this is negative 1 times x cubed. But x cubed is the original function, f of x. So this is really just negative f of x. And so what did we get? We saw that f of negative x equals negative f of x. That is, by definition, odd. So now, if we want to determine if this function is increasing or decreasing, as is, we really just kind of have to graph it. And this function, we might not do that with all of these functions. These other functions are a little trickier. We'll see if we can figure out a different approach, which I suspect we can. But Let's just go ahead and take a look at this one. This one's pretty simple. So if we plug in 1, we get 1, right? If we plug in 2, we get 2 cubed, which is going to be 8. So it's pretty obvious that as we plug in larger x values into x cubed, we get a larger output. Now, since this is an odd function, that tells us the rest of this graph is going to look like this reflection about the origin. So that tells you all the way from the left to right, this function is always increasing. So we can say increasing. There's actually maybe a little technicality here, which is not super important at the moment, but it will be more important in Calc 1. Notice that this graph levels out at 0. So it looks like it becomes horizontal. So technically, it is increasing except at x equals 0, where it levels out momentarily and then it starts increasing again. But if you said that this was increasing from looking at the graph, I wouldn't begrudge a student for that at this point. We have stronger tests that we can use for increasing or decreasing once we move into calculus that are a little bit more precise. Okay, so now let's take a look at this second function. F of x equals x to the 4th plus x squared. So we're going to plug in negative x. We get negative x to the 4th plus negative x squared. So again, this is equivalent to writing negative 1 to the 4th times x to the 4th plus negative 1 squared times x squared. And if I take negative 1 to the 4th power, I just get 1. And if I take negative 1 squared, I just get 1. But this is really just x to the 4th plus x squared. So this is the same thing as our original function. So what have we said here? We've said that f of negative x equals f of x. That by definition makes this an even function. So the only way really to consistently correctly identify if functions are even or odd is to know the definitions and apply them. There are some tricks sometimes with certain types of functions, but most of the time you just have to understand the definition, so it's really important to commit these definitions to memory. Now, as for determining if a function is increasing or decreasing, this one is a little bit trickier. So we may not quite be able to work this one out, and that's okay. Really, I just wanted to throw that in for some of these. But let's just see what happens here. So this is even. So if I have x to the 4th plus x squared, what do we know? If x is positive, then I'm going to get that x to the 4th is increasing and x squared is increasing. So actually, in this case, we can see that this function is increasing on the right-hand side. Now, I don't know exactly what this graph looks like, so I'm just going to say, oh, it's doing something like this, right? It's getting bigger, but it's an even function, so that means it's symmetric around the y-axis. So whatever it's doing on the right side, which it's clearly increasing since it's the sum of two increasing functions. If they're both getting bigger, then their sum is getting bigger with larger values of x. But on the left-hand side, when x values are negative, we're actually going to be getting a decreasing, and we can tell that from the symmetry across the y-axis. So in terms of over the whole domain, this one is neither increasing nor decreasing. Or you might say it's increasing from 0 to infinity and decreasing from negative infinity to 0. Depends on how specific you want to get. If I asked you, is the function strictly increasing or strictly decreasing, you would say neither. If I said, where is the function increasing, you'd say from 0 to infinity. If I said, where is it decreasing, you would say negative infinity to 0. All right, and the last part of this one. So I'm going to rewrite this here since we can't see it on screen anymore. F of x equals x cubed plus x squared. So we plug in negative x. That gives us negative x cubed plus negative x all squared. That's negative 1 cubed times x cubed plus negative 1 squared times x squared. Negative 1 cubed is negative 1. And negative 1 squared is positive 1. And notice, this is not the negative of f of x, because if I factored out a negative 1, I would get x cubed minus x squared. So this is not the negative of f of x. It's also not equal to f of x. So we can say this is not equal to f of x, and this is not equal to negative f of x. So this is neither. Now, I don't really have the tools right now, so I'm going to exclude part C from determining if it's increasing or decreasing. So that one would be pretty tricky. You could do a little bit of factoring and say, hey, this looks like f of x equals x squared times 1 plus x, or x plus 1, I should say. So in this case, you can tell that these are both increasing for positive x values. Plug in positive x values, the value gets bigger. But it becomes more complicated when you have negative x values, because then the x squared becomes a decreasing function. And this one would still be an increasing function, so you have that conflict between the two components. Now, we have more rigorous tools in calculus to determine if this is increasing or decreasing, but I don't have those available right now. So we're just going to not worry about increasing or decreasing for this. I certainly wouldn't assign any problems that required Calculus 1 techniques in my pre-calc class to evaluate, so you wouldn't have to worry about that. Okay, well, that's it for this section. Thanks for sticking around. Have a great day.